Welcome to Git for Data, data versioning for reproducible data science with Dolt. I checked, this isn't the longest title for a talk at the conference, but it is up, I think, in the top 3, so I did pretty good there. Let's get right into it, starting with who am I? My name is Zach Musgrave. I lead development on Dolt database, which is a new kind of SQL database that has Git-like version control semantics. So we're going to go into some detail about how that works later on in the talk. It's made by DoltHub, which is a 20-person database startup based out of Santa Monica. We also have a Seattle office where I'm from, so I'm very jet-lagged today. Before that, before working at DoltHub, I was at Google. You might remember me from the memes that I made. Before that, I was at Amazon, not Microsoft. I want to clear the record there. I've never worked at Microsoft. Disavow any Microsoft connection. So the next question is, what is Dolt? What is this weird database? So Dolt is this new way of approaching SQL databases that treats them like a Git repository. So all of the version control operations that you can do on a Git repository, you can do to a Dolt database. So that means you can create branches, merge those branches into each other. You can push the database to a remote. Somebody else can clone the database from that remote. So it enables this new kind of collaboration of the same sort that we've had for source control with Git for over a decade now to SQL databases. So we're the first database in the world to do this. We think it's pretty cool. Next question everyone always has is, why is it called Dolt? Are you calling me stupid? This is in our FAQ. We're not calling you stupid. You're very smart. I know because you came to my talk. For those not in on the joke, we named Dolt to pay homage to how Linus Torvalds is said to have named Git. So Git is British English slang for an unpleasant person or an idiot. So we kind of wanted to keep that joke going forward because Git is our main inspiration. So we wanted a short word that meant idiot, starting with D for data, and we ended up with Dolt. So the next question people have is, that sounds cool, but why are you doing this? We very frequently write technical blogs that we post to places like LinkedIn and Reddit and Twitter and so on. And very frequently we'll get this comment of you guys must be crazy. It's stupid to write your own database. It's 2022. You could use Postgres. You could use SQLite and go on top of them. You must be really dumb. We don't think we're dumb. We think we have a good reason for doing this, and we'll get into the technical details of why that is. But the short story is, when you want to build a database that has version control capabilities, you do have to start with first principles and build it from the ground up to store your data in a fundamentally different way to make that possible. And if there was any doubt, this is us on the left in this diagram. So before I get talking about any of that, I want to start off with a brief introduction of the history of data sharing for a couple different reasons. First, because I think it's kind of cool and interesting, and it kind of sets the stage for what's going to come next. But also because when we talk about reproducibility and version control in data science, we're always talking about this in the context of teams. When you're an individual, you can do whatever crazy stuff you want with your data. You can name the files final.1.csv, and no one's gonna call you on it. But when you work in a team setting and you actually need to collaborate with other people, when you want to share your results with other people, that's when this data sharing aspect becomes critical, and you can't just kind of make it up as you go along. So let's talk about this, starting in 1972, and all the way back to the days of Fortran. So Fortran at the time, the era we're talking about here, kind of occupied a similar niche to what Python does today, which is to say, if you were writing code to do some sort of numerical simulation for science or engineering or research, chances are you were writing Fortran back then. Of course, it's still used today, but the trend is towards Python, as everyone in this room understands. And the interesting thing about Fortran in the context of this talk is that they kind of invented, or at least standardized, what we now call the CSV file, common separated value. So everyone in this room has dealt with lots of CSV files, and you know all their foibles. A fun fact about CSV is that there wasn't really a spec when they invented it. It seemed kind of obvious and self-describing, which is one of the reasons it's caught on and persists to this day. But it also means that there's a lot of compatibility problems. So it's always kind of a gamble. If you export data from one file or from one program into CSV and then try to use it in some other context or with some other library that you download off GitHub, God help you. Anything might happen. If you have an embedded comment in a field, if you have a new line, if you have some binary characters or some Unicode characters, you just don't know what you're going to get. That's kind of par for the course, and people have learned to work around this problem with very clever solutions. So that was 1972. Here are some other pieces of technology that were kind of current in 1972, which, to make you feel old, was 50 years ago. So with the exception of that sweet muscle car, which I think we all can agree is still very current, the world's kind of moved on from most of the technology that we had, or that we considered relevant and current back in 1972, but not CSV. CSV is still around. And this isn't to say that old technology is useless or should universally be replaced. Other pieces of technology invented in the 70s include C and SQL, both of which are still very relevant and useful. But just to say that it's a little surprising when you stop and think about it, that something that's that old is still kind of a going standard for this particular domain. So of course, this did start to change. In the 90s, America signed on. This textbook kind of dates from that time. People kind of started getting home internet connections around 1995. So this kind of underscored the need for there to be modern data interchange formats. CSV wasn't going to fit anymore. And so this is the era when we got a couple new formats that are also still with us today, XML in 1998 and JSON in 2001. And the reason these became more popular and spread pretty far, pretty fast was the web services technology. Microsoft was pushing this at the time, Sun and Oracle. A lot of vendors got into the web service space and really kind of collaborated around these two formats. If you were around in kind of the mid-2000s, you remember how dominant XML was at the time. At the time, they were saying that XML is the only thing that Sun and Microsoft have ever agreed upon. Therefore, it's going to be with us until the heat death of the universe. But of course, we know that's not what happened. In fact, JSON came to completely dominate the text data representation of data to the extent that where it's rare to even see XML files anymore. If you encounter an XML file, it's probably to support some legacy application that was written in the mid-2000s. People aren't writing new applications that take XML anymore. And of course, this is for a lot of reasons. JSON is more compact. It's a much simpler language spec, so it's really easy to write a parser for it and put that into some other language, which has come along. But this is what happened. And that kind of brings us up to today. This is the state of play in 2022. If you're sharing data on the internet, you're doing it in one of these two formats. There's JSON or CSV, and the way you're sharing them is also often kind of primitive, which is to say you're zipping it up, you're making a tarball, and you're putting that thing somewhere on some hosted sharing site or a FTP drive or something and letting other people come and download it. This is starting to change a little bit, so people are starting to use version control on these textual data representations. They'll put them into a Git repository and then host that thing on GitHub the same way they would with their source code. And this is great, except that it doesn't really scale up very well. Once you have in the neighborhood of hundreds of megabytes of data, trying to host it in something like Git as text data is just going to make your life really challenging. Git wasn't designed to work with hundreds of megabytes of data, and there's, let alone gigabytes. And there's some workarounds with this, like Git LFS that host them in S3 and do other things. But when you resort to those things, you lose a lot of the benefits of what makes Git a compelling version control solution in the first place. And of course, this is a Python talk, so I'd be remiss to avoid mentioning that there are some other formats that people potentially sometimes use for sharing data. But I don't think that I'm out of bounds to say that these are kind of marginal and restricted to the Python community. People outside Python aren't sharing pickle files and pandas data frames on the web. One exception is SQLite. SQLite is a little compact SQL database representation that you can, for small data sets, check into GitHub like anything else. It is a binary file, so you don't get any of the get branch and merge logic that you would get if it was a text file. But people are doing this, and it has caught on to some extent. Okay, so that brings us up to speed on where we are with data sharing. And this is a topic near and dear to our hearts. When we set out to write Dolt, this was kind of the first use case we targeted. We decided, look, the way people are sharing data online is broken. These large text files don't scale up to be usable, and the binary formats make all the version control tools kind of unusable. So what do we do about this? We're going to talk about that in a little bit, but first I want to kind of give an overview of what I mean when I talk about reproducible data science, and talk about what data version control can add to a data science workflow. So I'm not a data scientist. I'm a software engineer. I'm writing a database. I'm not doing data analysis. But I do know some data scientists, and I've talked to them about this. So this is an outsider view, 30,000 foot understanding of what data science looks like from the outside. So I've divided up a data processing pipeline into these 4 stages here, which I'll talk about. The first one I'm calling source. This is basically just the phase where you haven't done any processing on raw data. So you're getting data. It could be training data that you're generating in-house and doing feature labeling on. It could be data that you're sourcing from online. You might be paying someone else to download some data sets, or just sourcing it from online in one of many, many different ways. Or increasingly, it could be the output from some other pipeline somewhere in your organization. I call out cleaning as a separate phase because anecdotally, this is kind of a major pain point in data science. I know that a few years ago, data scientists identified this as taking something like 80% of their time, just getting the data from some place that they didn't control and munging it until it was something usable that could be chewed on by the rest of their pipeline. So I'm hoping that has gotten better since the last time I looked at these polls, but my impression is that this is still a major pain point. So cleaning is the step that I'm calling making the data usable for the rest of the pipeline without introducing any sort of semantic changes, right? So you're not doing any analysis, you're not doing any real transformation. You're converting it from one format to another, you're fixing obvious errors, that sort of thing. Just making it so your pipeline can process it. Then we have this analyze phase, which is kind of useless because it's a black box. This is where all the actual logic happens, all the magic of machine learning or data analysis, whatever your specific domain is trying to accomplish, happens here. You're running arbitrary code written in Python or some other language. And this could be, arbitrarily complex. You could have, in fact, a directed graph of various sub-processes running whose inputs feed into one another. That's all great. I can't really speak to that because, again, I'm not a data scientist. But I do know that at the end of the day, you produce this result that you want to do something with. So in the ML context, your finished result is going to be something like a large language model that you can then build into a product or sell access to. If you're doing research of some sort or some kind of analysis, then you get some sort of aggregate result that you get when you crunch those numbers, and you want to share that thing with the world. So now I'm going to make a kind of bold claim, which I don't think is actually that controversial, which is that doing data science reproducibly requires some form of version control. And there's kind of a weak version of this claim and a strong version of this claim. The weak version is that in order for your data science to be reproducible, you must be able to, given a particular artifact that your data processing pipeline has produced, be able to identify via some system of metadata or tags or something where it came from. That is to say, you have to know exactly what version of your data input files were used at every step through the pipeline, and you have to know what version of your code was running at every step of the pipeline. If you know those two things, you can exactly reproduce the same run to figure out if it actually works the way you think it does and do further experimentation. If you don't know those things, you can't actually reproduce your results. I think this should be relatively uncontroversial. I've used these kind of Git-like commit hash numbers here to represent the idea that these things are snapshots of the data that are pointing off somewhere else. It doesn't have to be Git. The weak version of this claim, all you need is some system which is capable of identifying a particular set of data sources and code and giving that snapshot a name so that you can then refer to it and build that into your metadata. However, there's a stronger version of this claim, which is that all the benefits of version control that you get when you're doing software development at scale also apply to your data processing pipeline in ways that I think a lot of people haven't really considered, simply because the tools that we have available to us are so bad. They don't do what we want them to. So let's walk through the pipeline again and look at how version control actually helps the task at hand, how it helps make our lives as data scientists easier. I'm saying using the royal we, because again, I'm not actually a data scientist. So starting with the sourcing change here, or the sourcing stage rather, it's very common when you're running the data processing pipeline to want to always have the most up-to-date data. So for example, you're training a model to be able to pick stocks correctly. So you always want to have the most up-to-date stock market information being fed into your model. But this is kind of hazardous because you aren't in control of this data source. You can't vouch for whether it's accurate, how it's changing over time. So it's very common for people on the outside world to break you by introducing changes here. So they might add a column to their CSV file. They might drop a bunch of data that you were expecting later on in the pipeline. There's almost a unlimited number of ways that this can happen. The point is here, how can you actually even understand if it did happen? Because we're dealing with data files that are very large, and there's not really a great way to diff them efficiently using the data version control tools available for us. It makes even detecting these changes before they get farther down the pipeline pretty difficult. This is also very true in the cleaning phase, because if your cleanup script has an error, again, this is going to become an error that gets magnified as it flows downstream in the pipeline. how do you detect that early if you don't have good diffing capabilities? One workflow that we've seen work very well for people who have adopted Dolt as a version control tool for their data is using it to manage the state of their cleanup. So to give an example, if you have one branch of your data version control kind of pegged to the latest changes that are coming in from an outside source, you label that raw, and then you create a branch off of that, which has all the cleanup that you've done for every version of the raw data that comes in. It's possible to then merge those two branches into one another, with the result being that you have most of your data already cleaned up because most of the data stays the same between particular raw imports from time to time, but you get, and the data that hasn't been cleaned up yet kind of sticks out like a sore thumb, and you can identify that using the diff capabilities. In the analyze phase, like here, there's almost an unlimited number of things that can go wrong, and it's you do need these diff capabilities when you're doing kind of this debugging workflow. For code, we have something like Git. We can figure out what are the commits that have changed between this version of the code and this version of the code. What could I have done and introduced this error that I found? But again, there's nothing similar for the data. Doing that sort of diff analysis is really challenging. And finally here, at the end, when you get your results, again, how are you going to notice that something went wrong? How are you going to identify those problems? Hopefully before you share them with the rest of the world or build them into a product where you get bad results. If you do find some problem in the result that you're producing, are you confident that you can actually trace that problem all the way back upstream to figure out what caused it? What change in the code, what change in the data actually gave me a bad result? And the claim here is that version control helps you do these things, version control on your data, in exactly the same way that version control on your source code helps you debug problems in source code. So just to reiterate here, there's this need to kind of understand what has changed over time in your pipeline itself. So how have my source inputs changed over time? How has my code changed over time? We want to be able to answer those questions effectively. You also need to understand how the pipeline itself is changing over time. How the data is changing as it flows through the pipeline. So is it easy to understand what you did exactly between sourcing the data and cleaning it up? Is it easy to understand between any two particular phases of your pipeline what transformations were being applied? And if you can't answer these questions effectively, you're just going to have a really difficult time tracing backwards upstream to find the source of any problem that you have. So we aren't the first people to notice that this is an issue. There's been kind of an influx of tools into the data versioning space, and there's a lot of them available now. We wrote a blog about this called "So You Want Data Version Control." You search for data version control on Google, you'll see it's on the first page. You can click there and read about these. There's quite a lot of them available. I think there's actually probably been a few new ones that have spun up since we originally wrote this blog about a year and a half ago. And if you take one thing away from this talk, it would be you should really invest some time and effort into understanding at least what the problem in solution space is for data version control, because it is worth at least considering what it could add to your data science practice. But of course, I'm not here to talk about any of these particular products. I'm here to talk about Dolt because we think it's really cool and my company makes it. So relative to these other things, Dolt has unique capabilities as far as we're aware that aren't available in any other product. Specifically, we can do branches and merges on both the schema and data kind of at scale. So all these other data versioning products have things that they call branches and they have operations that they call merge, but they don't work the way that you would expect coming from a source control background. That is to say, if you and I have the same, or if you and I have both made changes to the same data file and on different branches, and then we try to merge those two changes together, that's a merge conflict. It doesn't matter if we change totally disjoint sets of data. The tool doesn't understand well enough how to merge those two things together. Dolt, this isn't the case. As long as you and I are editing the same table, we can, as long as we touch disjoint sets of rows, those two changes merge together quite cleanly. And we'll get a demo of that happening in just a minute. These other tools, a lot of them do handle large data in the sense that you can upload as large data files as you want to. They're just, most of them storing them in S3 or some other cloud storage solution. So it can scale up to quite large files. The problem is when you do that, you lose all the version control capabilities that you might have gotten if they were kind of a small manageable size. And with Dolt, this isn't the case. We have databases that are a quarter terabytes, and people are creating bigger ones every day that you can still do efficient diff and merge operations on. It was built from the ground up to enable that. Speaking of storing large files, Dolt is, I think, the only product that does some real form of structural sharing when considering snapshots. So if you have a particular set of files and you change a little bit of data and you want to make a new snapshot of that, ideally, the storage cost that you're paying is proportional to the size of the thing you changed. You're not doubling or tripling the size of your data storage bill every single time you make a new snapshot. And this is exactly what most of these tools do, because they don't understand the structure of the data well enough to be able to do an efficient diff operation, therefore do structural sharing. Finally, the thing that we think is really cool about this technology is that we, instead of trying to reinvent the wheel in terms of our interface, we just copied two relatively well understood and popular products. So for the version control stuff, Dolt works just like Git. And in fact, the command line is identical to Git. So if you know how to use Git, you already know how to use Dolt. There's no learning curve. You just type one word instead of the other. If you want to connect to Dolt like a SQL server, which is what the majority of our customers, how they use it, then any tool that speaks the MySQL dialect can just, and the MySQL wire protocol can just connect seamlessly. It's basically a drop-in replacement to MySQL. So in addition to Dolt, we also have DoltHub. These two products have the same relationship as Git and GitHub. So DoltHub is a website where you can host Dolt databases and adds features like creating forks, cloning those things. You can push and pull to it as a remote. You can open pull requests on data to make changes to someone else's data set, request that they merge it into the main branch, file issues against them, and so on and so forth. So when I say that we built this thing from the ground up to make diffs fast, this is kind of a slide that illustrates what I'm talking about here. So other database products and other data version control products do implement some version of a diff operation or a merge operation. The problem is it wasn't built to actually support that in an efficient manner. So what you see here is the result from SQLite 3, which recently added support for diffing two databases. We're looking for a single row change in a database of a varying size. And you can see quite clearly that SQLite kind of scales linearly with the size of the database, whereas Dolt scales basically with the size of the delta. It actually is, it's a little more complicated than that. There's a log factor in there somewhere. But the point is that we built this stuff from the ground up in order to make these operations fast, and you can really see it as the size of the data scales up. As you get into the tens and hundreds of millions of rows, it really makes a huge difference in being able to use these operations on a daily basis. The reason this is the case is because we built the data storage in this novel way, using this novel data structure that we call a trolley tree. We didn't invent this, but we think, the first to apply it to SQL tables and productize that into a version-controlled SQL database. So a trolley tree is a lot like a B tree, which is how most databases store their data. The difference is every node in a trolley tree has a cryptographic hash, similar to how Git identifies snapshots of files that you check in. What this means is that when you're comparing two databases that represent two versions or two snapshots of the same database, to compare them, you just start walking the root node in each one. And as you walk down the tree, anytime you encounter a child pointer that has the same cryptographic hash, you know that that entire subtree is completely identical and you can just skip over it. So this means that we can diff these two databases kind of proportional to the number of things that are different, rather than proportional to the size of the entire data set, which makes a huge difference. Okay, so now that you understand a little bit about Dolt and its capabilities, let's go ahead and do a quick demo where I show these things off. So starting with DoltHub on the right here, you can see I'm looking at this cities and states example database. And this is just a really tiny toy data set that I wrote in order to write a blog post about. I just chose some cities in the US that start with the letters A and B and put them into a database along with their populations according to Wikipedia. And I've cloned this thing on my laptop over here. So if I look at my current directory, I've already cloned it. I'm in the cities and states example directory. And if I type Dolt status, I can see the current branch that I have checked out. If I type Dolt log, I can see the commit history for this database. So these commands should look familiar. They're exactly the same commands as you would use if you were exploring a Git repository. You're typing the word Dolt instead of the word Git. Everything else works exactly the same. So for this exercise, let's figure out how to add some data to this data set and make some changes and then put them up on DoltHub. So in the directory above me, I've got this CSV file, cities.csv, and it's got a bunch of cities starting with the letter C. So I'm going to add some C cities to this database and update it. The first thing I want to do is create a new branch to work on, because it's kind of a faux pas to work directly on main in Dolt and in Git. So I'm going to call this thing zacmu/new cities. And again, this command should look very familiar because it's exactly the same as the command you would type in Git, switch to a new branch. So once I have this new branch, I'm going to import that table. So the command here doesn't have a Git equivalent. Dolt table import cities branch. Okay, so it tells me that I have processed 10 rows, and if I want to see what changed, I run this dolt diff command, and I get this output showing me, hey, you've added these 10 rows to your data sets. Here's what they are. Great, let's go ahead and commit those things. So I'm going to run the dolt commit command and say new cities. Okay, so I have created a new commit. There's my new commit hash and the message I typed in. And if I run the dolt log command, I can see it has a new commit there. Okay, so now that I've done that, let's go ahead and do some sort of collaborative workflow where I'm going to make some changes on 2 different branches and then merge them back together. So the first thing I want to do is create those 2 branches. I'll call them Zacmu A and Zacmu B, and then check one of them out. Check out the A branch first. Run dolt status to make sure I'm on the branch that I think I am. So in order to edit the database, I'm going to pop into this interactive SQL shell that ships with the product. I just type dolt SQL, and now I'm in working on the database. If I select star from cities, I can see everything that's in there. So all my changes, A, B, and C. Now I'm going to run an update statement to update the populations of these cities. So these came from Wikipedia. I'm going to update the population a little bit in order to reflect how it's grown since the last census. Just add 2% to everything across the board, but only where the city starts with A. Okay, so exit out of the shell, and if I run the dolt diff command, here's the changes I made, old row and new row. It looks just very similar to Git output when you're running git diff. So I just updated the populations of all the cities that start with A, and I'm going to go ahead and commit this thing and say updated A pops. It's probably not the Aspen you think of, probably a different Aspen. Okay, so now that I've done that, let's go ahead and check out my other branch. Zacmu/B. I'm going to do the exact same thing. Run dolt SQL, and then run that same update statement, but on the B cities. And back on the command line, you can see that my diff only encompasses those B cities. I'll go ahead and check that in the same way I did before. Okay, great. Now let's switch back to the original branch we were working on, which is called Zacmu/new cities. Spell it right. Spelled my own name wrong. So to merge those in, I'm just going to type the dolt merge command, and this works exactly the same as git merge. I just give it a branch name, and it merges that branch into the one that I'm on. So we'll start with the A1. This is a fast forward merge because there aren't any intervening commits between the commit histories there. And then let's do the B1. It's not a fast forward merge because there is a intervening commit. And then I can run the dolt log command to see what's changed. So here I see I created a merge commit, and then here's the commit I made on the B branch and the one I made on the A branch. And I can diff these as well. If I run dolt diff on the thing before head, this is the B changes. 2 before head includes the A and B changes, and 3 before head includes the A and B changes, as well as adding the C cities. And of course, these diff commands take exactly the same kind of arguments that they do on Git. Great. So now that I've made my changes, I want to share them with the rest of the world. So I'm going to push them back to my remote, which is DoltHub. Again, this command works exactly the same as it does on Git. I'm going to say push origin and then the name of the branch I want to push to. Hopefully this works. This is the live demo portion. Very slow upload in the Microsoft building, but it did go through. So now if I refresh the page, I can see that there's the Zacmu/new cities branch. And if I load that branch, now I'm looking at the file as it exists, or sorry, the table as it exists on that branch. If I want to go and merge that thing back into the main branch, I can open a pull request to do so. So my base branch is going to be, I'm going to merge into main from Zacmu new cities. Just give it a description. Create the pull request. So now I've got this pull request sitting and pending, and it's exactly the same workflow, a little bit stripped down that you would see on GitHub in order to do a code review. Now it's a data review. So I can look at the diff, I can see exactly what's changed, what changes are being proposed to merge from the source branch into my main branch. I can pass this off to a colleague and say, hey, double check me on this, make sure everything works the way that I think it should. They can leave comments, we can go back and forth, and I can make additional changes, but you get the idea. So one thing that we think is really cool that we've built using this workflow that I just demoed is our bounties program. So we had this idea, we wanted to crowdsource open data sets. So we wanted to kind of put out the call on social media and say, hey, we want everybody who's interested in this particular area to help us scrape public data and compose it into a single unified data set for other people to use and consume. So we've done this for about a year and a half now. I think we've done about 15 of these bounties. And the idea is that we pay them out based proportionally on how much people contribute. So the way this works is everyone who wants to participate goes and makes a fork of the particular database that the bounty is hosted on DoltHub, and then they clone that fork to their local device, and then start making their edits using whatever tools they want, importing CSV files, issuing SQL updates, connecting SQL workbenches to the tool, whatever they want to do. When they've made all their changes, they upload that back to DoltHub using the push command, and then open a pull request. And then we actually employ a full-time employee whose job it is to just be the referee and administer these bounties to decide of these pull requests, which ones are good enough quality to make it into the final data sets. And then at the end of the day, we have this list like the one you see on the left. This is the scoreboard where we can, because we have a commit graph and a commit history, we can identify very accurately how much of the data set is attributed to each individual who participated in the bounty. So we pay out $10,000 for this particular bounty overall, and we divide it up based on how many lines of the final data set they contributed. So like I said, we've done about 15 of these so far. It's been going really well, and we've got some really cool data sets that we've produced, like the graph on the right, which shows kind of the long tail of what you might expect to pay for a C-section in America. So if you want to learn more about Dolt and DoltHub, check out our GitHub repository first and foremost. It's DoltHub/Dolt. Download the tool. It's free and open source. Get started using it. Give us a star. We always like when people do that. If you want to kind of follow our development progress, you can go check out our blog on dolthub.com/blog and also play around and see what other open data sources people have uploaded to DoltHub. That's all I've got for you. Open up to questions.
Great. Any questions? I'm going to pass you the mic.
Thank you so much for the talk, and I'm fascinated by your approach to data version control. I'm curious about whether it's order sensitive or does it need to be aware of what primary keys are, because it could be the same contents, it's just the order was shifted.
Yep. So the question was, does it work with tables that have primary keys and ones that don't have keys? The answer is yes, but you do lose some. You lose the ability to understand what's changed in a given row. So without a primary key, there's no such thing as a row identity. To the database, changing a cell in a particular row looks the same as if you deleted that row and added a new one. You can't tell the difference because it doesn't have row identity. But it does, the diff operations do work. It's just everything looks like an add delete as opposed to a modification.
So if you do define it, there is a way of defining primary keys, and that can be smarter, is what you're saying?
Right. So if you have primary keys, then the diffs are richer because we know that this particular row, the following cells change. Here are their old values. Here are their new values. Whereas if you don't have a primary key, we can't tell the difference between that operation and a add delete.
Cool.
Yeah. Thank you so much. Is there any equivalent of like git ignore and pre-commit hook for this?
The question was, is there a git ignore equivalent? There isn't yet. This is on our future roadmap, but we haven't implemented it yet. If you want to tell us what you're doing and why it's important, come hang out with us on our Discord channel and talk to us, and we can get a schedule.
Okay. Thank you so much. And I assume like it's the same for like a pre-commit hook, right?
We don't have pre-commit hooks. We do have what we call webhooks on DoltHub. So after you push, it'll run some arbitrary webhook that you set up with HTTP, but it's not the same as a pre-commit hook like you're asking. That would be another feature request.
Okay, thank you so much.
So I'm really fascinated by your building of this tool and having it mirror GitHub in the problem space. Obviously, it's a super interesting problem to solve, and you've committed a lot of time to solving it. So I'm wondering, what specific problem did you encounter that was so compelling that made you want to build all of this infrastructure? Like, what's your villain origin story for doing Dolt?
Okay, this is an interesting question, but I'll try to keep it brief. So the company was founded by some ex-Snap employees that I happened to work with back at Amazon that lured me into this whole thing. And when we founded the company, the idea was not to be a version control database. It was just to be data version control. The observation was there's a lot of data changing hands on the internet, a growing amount every year. Some people estimate that this is like a $50 billion business currently. But the way that they're doing this is they're literally emailing spreadsheets back and forth. So they're like, we decided we wanted to kind of figure out if we could bootstrap some sort of real data sharing hub on the internet. And that's how Git started. The SQL aspect of it and the database aspect of it kind of came over time. And that's kind of the niche and the product market fit that we found. Most of the people who are actually paying us money to use the product are using it to build database applications. They're not using the data sharing use case. The data sharing stuff I think is really cool and it sells the product well. People get excited about it. But for us, it's that we think that will catch on. People will be using DoltHub to share and collaborate on open data, but it's just taking longer. I think that it's taking a long time to catch on, longer than we would like, I would say.
We got a question back here.
Hi, thanks for the talk. I was wondering, is there a way to sync your commits to DoltHub with your Git commits? Because it's not just the data that changes, your training pipelines could change as well. So when you check out a particular commit in Git, you'd want to make sure that you have the right data for that pipeline.
Yep, there is a way. We vend a tool that does this, but it hasn't seen like rapid adoption, I would say. So it's not super well documented. But the way you implement it in Git is they call this a smudge and a filter, I think they call it. The terminology is strange, but basically you give Git a little pointer into this other data source. This is how Git LFS works. So that when you run git pull, you're not only pulling the local data, but it's using that hook to pull down data from some other source. In the case of Git LFS, it pulls it down from S3. In the hook that we implemented, it pulls down that data set locally from the DoltHub remote. So there is a way to do this. It's a little bit cumbersome, and we're looking for better techniques to actually make it work better.
Okay, one more back here.
Any interest or plans in supporting NoSQL databases?
So if you squint at Dolt, it is a NoSQL database. You just don't run the database server, right? Like this is kind of how pandas and data frames and other things work. Is you take the entire database and load it into memory and run whatever transformations you want. And people are using Dolt that way. But in terms of the database features that we're developing, we're definitely on the side of SQL. That's kind of the direction we've chosen.
Are people using it for analytics? I guess the storage format appears very row-based, and which seems kind of integral to the actual product itself, because if you're using primary keys to diff, then fast single searches are important.
Yep.
So I'm just kind of wondering, it's kind of related to his question, but like,
sure.
I'm just wondering if people are doing that.
Right. So people are using it for analytics. I think the OLTP use case is the more common one. But it does run large queries. It's not optimized for them because like it is row-based. It's not a columnar store the way that you would find in a lot of other data warehouse products. It does work for that. It's just the performance is not going to be there. So we've got the kind of the correctness in terms of being able to run large analytical queries. But in terms of being able to compete with something like Snowflake, which is a columnar store, we're not there yet. At some point, we may offer a columnar version of the product in order to specifically address this use case.
Are there any special schema design considerations when you have mergeability of your database?
There are. One thing that we ran into really early is that people in the MySQL world really like this auto increment function. In Postgres, they call them sequences, but it's a way to get an automatic monotonically increasing ID in a particular table. When you do this with different tables, it becomes kind of a disaster because my branch and your branch have a different idea of what row one is. So we've kind of we do support this. The way we supported it was making this auto increment counter go up globally across all branches when you're running the server, as opposed to individually for each branch to avoid the merge conflicts. But it's still not a great idea most of the time. What you want is if you and I have a copy of the database and we both make the same set of insert statements, we should end up with the same database. It should be identical down to the hash. And there's things you can do with like generating the values of columns that violate that assumption. And the tool still works. It just you lose some of the cool use cases that you could do. You get merge conflicts where you wouldn't have wanted them.
Another question right here.
Somewhat related, how much of like the primary key setup, some of like the schema idiosyncrasies to get this to work, how much of that is sort of like built in and abstracted from the users? Like how aware do you have to be of some of these things in order to get Dolt to actually function properly?
So if you're doing the kind of the data import case, you have to be aware enough about the structure of your data in order to tell Dolt what the primary key is. That's kind of the table stakes. And you have to know a little bit of SQL because we have tools that try to infer the schema based on a CSV file and stuff, but they're not perfect. For example, they'll choose like the wrong size for a varchar column and so on. So you do need to be able to know how to run a create table statement in SQL. But beyond that, everything kind of just works the way that you should. We've done a lot of work in getting compatibility to work with basically every MySQL tool and library under the sun. So these days, it's surprising if somebody spins up some random MySQL library to connect to the database and it doesn't work. Most of the time, it just does what it should.
You may have actually just answered my question, but I was curious, kind of come back to the analytics use case. Is there, you're following MySQL's dialect, is there anything you had to add on top of that to kind of handle things like maybe joining against the same data set but at a different snapshot in time or something? Or is that something that's supported within the existing dialect?
Right. So it didn't require any extensions to the dialect per se. I'll generalize your question and say, how do you access the kind of version control capabilities within a SQL context, right? So instead of checking out a branch on the command line and then querying that branch, you can actually do that within a SQL session. So there's this SQL extension that was added in like 2011 where you can use the as of keyword in a query. So in Dolt, we implement this to, if you say select star from my table as of, and then give it the name of a branch. Now you're looking at that. You're looking at the data from that branch for that query. You can access all the functionality from the command line through a combination of system tables and stored procedures to do things like make commits, push them to remotes, diff to commits. Those are all available in the SQL context, but it's a lot of stuff to demo, so I didn't really have time to squeeze it all in there.
We have one more question.
Yeah, so I was just trying to understand. So each table is like corresponds to a file. Is that like in Git? Is that correct?
That's generally speaking, CSV files kind of map each of them to a table. It's difficult to because they have one schema throughout, right? So that's typically how people map their data. Yep, all the branching capabilities apply to all the tables in the database. So every branch, and in fact, you can have branches where some branches contain a particular table or have a different schema on a particular table than other branches, and that's all fine and works the way you would expect. Right. If you're coming from a data analysis world where you're used to feeding some CSV files into pandas and shooting up some result, the right mental model is that each of those files is now a table.